So what is the first one? What is the first condition? Size of cation and anion. Size of cation and anion. In this case, same number of positives and or else same number of negatives are going to lose. Same number of cations or same number of anions will go out from the lattice. So obviously, size of cation is equal to size of anion. Comparably, both are same, equal. In case of Schottky defect, I am talking about. So size of cation comparable to size of anion, because same number of cations and same number of anions need to go out. Size of cation and anion both are comparable. But where about Frankel defect? Anion size of anion is far greater than size of cation. Why? Okay, in definition we discussed about either anion or cation goes into interstitial positions in Frankel defect. But usually, actually, it is not anion generally goes. It is the cation generally shifts into interstitial positions, interstitial site, or else we can say. If cation size is too small, then it will go and arrange into the interstitial position very easily. That is the one simple common point. Here what I am saying, Frankel defect, either cation or anion shifts its position to interstitial positions. But there is in general, but actually say cation, the one who goes and sits in the interstitial side. If at all the cation size is small, then it is easily can go and sits in the interstitial positions. If the size of the cation is big, then this sort of defect is also not possible to happen. So obviously, this cation size should be less so that it can go and sit into a void or interstitial site. So this is the basic difference between Schottky defect and Frankel defect whenever we consider the size of cation and anion. Then coordination number. What is the coordination number? Number of neighboring atoms touches one atom. When this coordination number will be high, when the size of cation is more number of anions should surround the positive charge. So coordination number will be high in case of Schottky defect. We are saying that cation size is comparably equal to anion, or else we can say cation size is bigger one. When it is comparable to anions, means cation size is somewhat big. So obviously bigger cation is surrounded by so many anions. So coordination number is high. But here what we are saying, cation size is small so that it can go and fit into voids very easily. So obviously coordination number of small cation will be low. Basing on this size only, coordination number differs. Next, if you see the examples here, Schottky defect is shown by NaCl, KCl, KBr, and in this Frankel defect, AgCl, by experiments we came to know all these things, AgCl and ZnX. But one such compound is there which shows both the Schottky defect and Frankel defect, that is silver bromide, AgBr. Only up to examples wise you require these ones. So So NaCl, KCr, Kb or all or cesium chloride. These all shows Schottky defect, whereas ACCl, ZNS shows Frankel defect. One ionic compound which shows both these two things is AgBr, that is silver bromide. This is about defects in solids. In stoichiometric case, stoichiometric case, stoichiometric, vacant, interstitial, Schottky, Frankel. Then let's go to non-stoichiometric. This is also divided into two parts: metal excess deficiency and metal excess defect and metal deficiency defect.